Konnichiwa.
I think one of the assignments is missing from Learning Suite, but I'll have to add that after class.
Okay. All right. Who'd like to start us off with a prayer today? Go ahead.
Our Heavenly Father, for this day, we're grateful we can come to God us today to be able to learn more. And please bless us as we listen to Brother Corey, that we can understand what he's saying and make sense of it in our heads so that we can do it on our own. And we're so grateful for the opportunity to learn each more every day. And we say this in Jesus Christ, amen.
Thank you. Well, it's great to be back. Missed you guys on Friday. But let's hear it for Brinley, who covered class for us. I think you did a great job. I know you guys would rather have the TAs every day than me, right? One semester. Someone said yeah. One time, I had 3 TAs, and I got rated by a student as being the 5th best TA in the class. And number 4, Patrick, does the videos that you guys watch, was above me somewhere up there. So, yeah. All right. So, a few things. Your tests are up. The test scores and the tests are up on Learning Suite. You can go see what how you did. You can actually go see the scanned-in version of the exams. Please get on, take a look, make sure there were no obvious errors in the scoring. Today is also the withdraw deadline. So you can withdraw from the class. It's still a possibility. If you're considering that, you should come talk to me or talk to some academic advisor to make sure that it's not going to hurt you later on. So if you're not careful, you can lose scholarships, you can get kicked out of housing, or you can get kicked out of the country if you're an international student. It depends on different things, but sometimes you have to be full-time, and if you drop this class, you're no longer full-time, and then it has implications. If you withdraw, just FYI, if you withdraw and you're passing the class, you get a W on your transcript. It does not, and it doesn't get factored into your GPA at all. And if you withdraw and you're failing, you get a WE, and I think it counts as a fail in your GPA. I think that's the way it works. But if you have a few W's on the transcript, it's usually not that big a deal. If you have a lot of W's, then that's usually a red flag for employers or grad schools. But just FYI. Okay. So today we're going to spend we're going to do some more work on the root test and the ratio test, and if we have time, I will teach you my favorite test that's not in the book. If we don't get it today, I'll teach it to you next time. Ryan?
I was just going to ask the average test. I realized
Oh, the average was 73.5 for all sections, and we were like 74.1 or something. Like of the three large ones, yeah, they were all pretty close, but we were the largest this time. Last time we were in the middle. So, but good job. Way to beat. It was a little lower. Usually in 113, the second exam is the highest. But if I remember right, this was what was the average last time? Was it like 76? Yeah. So the average was a little bit lower. It does depend. I mean, just depends on how hard the tests are. But usually it's a easy test. Okay. So when you take about 15 minutes and work on these, do as many of them as you can do. Okay. Doing root test and ratio test. So which of these converge and not, and why? So.
What was the second problem?
They're already there.
So like, it's just the 1 plus 1 the rest. Squared. So probably nothing. And squared. Well, Oh, you just went through
All right. Quickly, what seems like would be the best test for number one? The root test. So the root test is not as flexible. I mean, it's not as what's the word? You can't apply it to as many situations, but when you can use it, it saves you a lot of work. So try to do the root test if you can, other than the ratio test, because it can save you a lot of work. So here, yeah, you'd think root test, okay? Or root factorial. Just kidding. Okay, how about the second one? Root, you'd think, yeah, root, you've just got powers of n, or here in this case n squared, so you try root. What about 3? So ratio, what gives it away that you should do ratio? The factorial, okay? And what about 4? I don't know if many of you got to 4. We can use the ratio test works out here. Well, here, you don't have a general form to write down for a root. So, okay. So let's look at number 1. Okay, so we're going to try the root test. So we're going to take the limit as n goes to infinity, the nth root of the absolute value of 1 over the natural log of n to the n. So, of course, so I've put on the absolute value to remind you that the root tests and ratio tests, they test for absolute convergence. Okay, if the signs are changing, we've got problems. So it only tests for absolute convergence. In this particular case, we're only going to have positive values, at least if we start at n equals, as long as we start with n larger than 1, so n equals 2 maybe. So it doesn't impact us a lot right here. Okay, so we simplify these. The nth root of 1. Brinley, did you go through these, like the nth root of a constant and the nth root of n? Did you talk about these, Brinley? The limit? Okay. Yeah, they probably came up in some of your examples, right? So if I take the nth root of a constant, as n goes to infinity, what do I get? You're going to end up with c to the 0, which is just 1. So it approaches 1 in the limit. What about the nth root of n? It's an indeterminate form. It's an infinity to the 0. You have to take the natural log, do our natural log trick, and pull it down, but we won't take time to do that right now. But that also ends up being 1. So how about the limit as n goes to infinity of the nth root of n to some power? I mean, this power could be like 1,000,000, 1,000,000,000. What do you think that's going to be? It's also 1. That nth root just really drives it down to 1. So so those are good things to keep in mind. So often this bottom one here, like the nth root of n squared, you know it's going to go to 1, for example. Okay, we end up with the limit as n goes to infinity of 1 over the natural log of n. Where does that go to? It's form 1 over infinity, which is 0. So what does that tell us? Converge, diverge, inconclusive. So this converges because 0 is less than 1, right? If we set up this limit and we get a number less than 1, then it converges. So it converges by the root test. Okay. Let's go to number 2. All right. We already also said this also looks like we should try the root test. So we set up the limit as n goes to infinity of the nth root of 1 plus 1 over n to the n squared. Some people were thinking about the n squared as 2n. That's different. This isn't something to the nth power times that something to the nth power. That would be the something to the 2n. This is 1 plus 1 over n to the nth power, all to the nth power. So that's what the n squared. That's what the n squared means. So we can use that. Or you can think about it this way. That's 1 plus 1 over n to the n squared divided by n. Right, this root here I could think of as 1 over n. So 1 over nth power. So that simplifies. Limit as n goes to infinity. 1 plus 1 over n to the n. And what does that equal? It's an indeterminate form, but it is a limit you guys have seen before. This is e. Okay? So it is an indeterminate form. We're not going to take time to do that because there's a problem we're going to bump into where we're going to use the same technique. So this is the problem where you rewrite it as e to the natural log of the limit of 1 plus 1 over n to the n as n goes to infinity. And so you eventually end up with, find it that it's e to the 1. So, okay. Okay, so here, right, if you recognize that that's e, awesome. If not, hopefully you'd recognize it as 1 to the infinity, which is an indeterminate form. And then you've got to think, got to do that fancy natural log rule so I can pull things down and eventually get into L'Hopital's rule. We will do that in another problem. So let's go to number 3. Let's move these down. Oops. Okay, what test should we use here? Ratio. If you see factorials, ratio is usually your best bet. So let's start setting up with the ratio. So the ratio test, you take the limit as n goes to infinity of the a n plus first term, absolute value, over the a nth term. Okay? And see what that limit is. If the limit is, just like the ratio test, if L is less than 1, it converges. If L equals 1, it's inconclusive. And if L is greater than 1, then it diverges. So let's set this up. The n plus first term, n plus 1 factorial over n plus 1 to the n plus 1 over n factorial. Let's move that down a little bit further. Get that out of our way. Almost. That just became problem 1. n to the n. Limit as n goes to infinity. And going to invert and multiply, start simplifying here. I can rewrite this one as n plus 1 times n factorial. I can rewrite the denominator as n plus 1 to the n times n plus 1. And then I will have here, if I invert and multiply, end up with n to the n over n factorial. And n factorials cancel out there. My n plus 1 and this n plus 1 cancel out. And I end up with the limit as n goes to infinity of n to the n over n plus 1 to the n. Okay. So that may have gone a little fast. So let's stop for a second and make sure you're up with me. So, any questions? It's because Brinley taught you so well. Yes?
So, n plus 1 factorial, why is that n plus 1 factorial?
Oh, great. Okay, I wasn't sure how much of these you guys did last time. So, n factorial is n times n minus 1 times n minus 2 times n minus 3, right? Down to 3 times 2 times 1. So at any case, I could rewrite n factorial as n times all of this. I could write as n minus 1 factorial, right? Or I should just do 5 factorial is the same as 5 times 4 times 3 times 2 times 1. But all of these I could rewrite as 4 factorial. So 5 times 4 factorial. That's going to be the same as 5 factorial. So I'm just using that trick. So because I have, if I have n plus 1 factorial, then I have n plus 1, but then I've got to go down 1. And going down 1 is just going to give me n. Then I go down 1 again, n minus 1. Then I got to go down 1 again, n minus 2, etc. So here on out, I just have n factorial. So, okay. All right. Any other questions so far with this one? All right. I know a lot of you got to here, and then your big question was where do we go from there, right? Let's rewrite this as, I'm going to write it all to the nth power. So limit as n goes to infinity of n over n plus 1 to the nth power. Okay, what ideas do we have here? Repeat the step that we skipped on the last problem, right? This is what form is this? It's not geometric because it seems it's close to geometric, but this is not a constant. For it to be geometric, the common ratio has to be constant. This thing we're multiplying by each time changes. So, but it seems like kind of geometric in form. Okay, someone else raise their hand.
Can we multiply top and bottom by 1 over n?
Multiply top and bottom by 1 over n. Oh, and see if that simplifies things inside. We could. I don't know what happens with that. So then you get a 1 over 1. I'm sorry, you get a 1. Come on, eraser. 1 over 1 plus 1 over n. Right. So you should be thinking like, hey, that looks really nice now. Because here, let me write out what we did right there. So I'm going to multiply the numerator and the denominator by 1 over n inside the nth power. So this is n over n plus 1, and so I get the 1 over 1 plus 1 over n all to the nth power limit, and that's going to be 1 to the n over 1 plus 1 over n to the n. Limit as n goes to infinity, and I'll do the numerator. What's the denominator? E. Yep. It is. So, yeah, it is. This is, but we redid it so it was 1 over 1 to the infinity. But this is of the form that we already know. I think we already know that this particular. Oh, that's if you have if it's actually 1, then no. You just have 1 times 1 times 1. If it's something going to 1, then that's indeterminate. Gotcha. So 1 over e. So Brian asked, was there another way we were going to do it? Yes, this is slicker than the way I was going to do it. So nice job. Okay, but because this is of the form here, this is of the form 1 to the infinity. And so how do we handle those forms? You take the natural log. So we're going to rewrite that as e, limit as n goes to infinity, of the natural log of n over n plus 1 all to the nth power. But then I can take that n out front, and you get now we have a form of an infinity times a 0. And then how do we handle those? Yeah, let's rewrite that n as 1 over n. Okay. And then you can do L'Hopital's rule. And you end up getting a negative 1. So you get e to the minus 1 when you do L'Hopital's rule. Okay. You guys want me to do it? You want me to work it out? Okay. Let's work it out. Okay. It's not that bad. You do have to do the quotient rule though. Okay. So we're going to take the derivative of the natural log. I said we will have to. Yeah. So the derivative of the natural log, so we're doing, will be 1 over, 1 over n plus 1 times, and this is where we have to do the quotient rule. So we have to do the chain rule and then the quotient rule. So the derivative of the numerator, which is 1, times the denominator minus the numerator times the derivative of the denominator, which is 1, all over n plus 1 squared. And then the denominator, the derivative of the denominator is a minus 1 over n squared. Okay. So this, L'Hopital's. And then what do you end up with? It looks crazy, doesn't it? But let's invert this piece so you get an n. Oof. N plus 1 over n. Here this n and this, this n and this n plus 1 add to 0, so you just end up with 1 over n plus 1, positive, squared. And then here you end up with a minus n squared over 1. There. Whew. Well, in the limit, that goes to 1, and your n squared over n plus 1 just do L'Hopital's rule a couple times, and that's going to go to a minus 1. So, but all of that is raised to the e. Forgot to carry that e along. So you get e to the minus 1 that way too. So either way. But I like the first way. Saved us some work. Yes? This one? This one? Oh. Like this one? That's the quotient rule. I have to do the chain rule and the quotient rule when when I'm taking the derivative of this one here. So the derivative of natural log is 1 over that something, and then I have to take the derivative of that something, but I've got that quotient there, so I have to do the quotient rule. So, okay. All right. So does this converge or diverge? It converges because, so 1 over e is less than 1, so we get converges absolutely by the ratio test. Now, I've really moved this like way too many times, haven't I? So look at what we just found. We found that the ratio we actually found a relationship between n factorial and n to the n. So there's this weird relationship between n factorial and n to the n. E comes up somewhere in here. And the ratio that we found from term to term is related to e. And you can actually use this, mathematicians use this to approximate n factorial. So start off by taking n to the n and dividing by e to the n. We saw that in the limit, in the ratio of the terms, n to the n is about e times as much. Ours was, the way we set it up, notice that n to the n was in the denominator here. Okay? N to the n was in the denominator, and we ended up with 1 over e. So the ratio of these to go from one term to the next term, it's about like multiplying by 1 over e, which is weird. But that's not the weirdest thing here. If you want to make this a better approximation, you multiply it by this. The square root of 2 pi n. So here you have another formula, another expression that has e and pi in there. We didn't do the probability section, but if you know much about the normal distribution, to write out the normal distribution, it actually has e and pi in there, and it actually has 2 pi times a variable sigma in there. So it has the square root of 2 pi in there also. So it's kind of crazy. So this is called Stirling's approximation. And this allows you, I know you guys have only thought about factorials in terms of whole numbers. right? 5 factorial, 6 factorial. This actually allows you to calculate, or at least approximate, factorials for non-whole numbers. Like, what's 2.3 factorial? You might think, like, why would anyone ever wonder about that? Well, that's what geeky mathematicians do. But it actually comes up in lots of problems, trying to figure out what non-whole factorial numbers are. And that's only an approximation. This is the way it's defined. It's defined with something called the gamma function. You ready for this? And gamma of n, this is not exactly n factorial. This is n minus 1 factorial. So this is called the gamma function. So those of you that go into statistics, you'll bump into a gamma distribution. Those of you that go into physics, this is the basis for string theory. So it comes up in some crazy places. But this is actually how you can find exactly what factorials are for this is how factorials are defined for non-whole numbers. So, and this is actually something that you guys can actually calculate now for certain values. For example, if you wanted to know what gamma of 5 was, which is 4 factorial, then, oops, it's supposed to be infinity, not an 8. X to the 5th e to the minus x dx. And all you have to do is do the improper integral here. And you would have to do parts about 5 times. So, 5 times. But it's crazy that integral, that strange curve that goes, looks something like this, depends on what your n is. If you plug in a whole number, it equals exactly that number, minus 1 factorial. So if you plug in 6, well, if you plug in 5 factorial, you get this thing, it would equal exactly 24, because that's 4 times 3 times 3 times 1. All right. Very crazy. All right. It's going to be on the exam. No, I'm just kidding. Okay. All right, let's do the 4th problem. So this problem is different than the other ones. It's not even written out as a series with sigma notation, at least. And here it helps to write out. One of the keys here is to write this out so you know what the nth multiple is in the denominator and in the numerator. So in your nth term, what would this number be? And in your nth term, what would that number be? So in the numerator, notice that each time that we're going to find a pattern, we get 2, 5, 8. What number is going to be next? If we need 11, and then 14, and then 17, etc., right? So if this was n equals 1 right here, what's going to be my nth term? What's the difference in each of these? I'll show you a nice trick. So if I look at 3n, the sequence of 3n is 3, 6, 9, 12, 15, etc. How off am I from this one? 1 too much, so let's just subtract 1. So 3n minus 1 will give me my nth term. Okay. So how about in the denominator? In the denominator, I have 3, 5, 7. That's the sequence. What's the difference in each of these? The difference is 2. So I'm going to compare it to 2n. 2n is 2, 4, 6, 8, 10, etc. How far off am I on each of these? I have to go up 1. So this one will be 2n plus 1. Okay? And now you're thinking like, Brother Corey, that looks terrible and I have no idea what to do from here. But with this general term, we can actually start doing a ratio test. Okay? So, oops. Come on. There we go. So there is our nth term. We need to divide the nth term into the n plus first term. Okay. I'm going to get 3n minus 1, and then I'll get 3n plus 1 minus 1, and then I will have 3 times 5 times 7 dot 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 2n plus 1 2n plus 1 plus 1. Okay, I'm going to let you guys work on it from there. What would you do from here? Take the limit as n goes to infinity. There's our ratio. Yeah. Okay, we'll start with this next time. Have a great day.